So let's look now at a heap data structure. So a heap is visualized as a binary tree and it's typically implemented, so typically as an array. Okay, so this means in memory it's really stored as an array, which is really sort of a simple data structure itself, but it's stored in such a way that we can visualize it as a binary tree. Now at this point you probably have seen a binary search tree. What will be the difference? Before we go into what it means to be a heap, let's look at this again. So let's say I have this data. So 4, 2, 1, 3. This right here. Or I have this. Both of these are binary search trees because the values to the left of a parent, that is the left child, and everything descending from that, has a value that's less than or equal to the parent, and everything to the right is greater than. So 2 is less than or equal to 4, 1 is less than or equal to 2, 3 is greater than 2 because it's on the right, 5 is less than or equal to 6, 7 is greater than 6, right? But like I said, this is also technically a binary search tree. 2 is greater than 1, 3 is greater than 2, all the way down. Now we prefer this version in general because it minimizes how far down in terms of levels I have to go to find something versus this. This is really just a list. But technically they both meet the binary search property. That is, these relationships. Okay, the left child is less than or equal, the right child is greater than, at least by convention, right? So this says that there's nothing about balance incorporated into the definition of a binary search tree, but we prefer balance in terms of improving performance for finding something. What about a heap? Now heaps come in basically two forms. A max heap and a min heap. What I'm going to discuss is a max heap. So a max heap is also a binary tree, we already said that earlier, that has these properties. One has what's called the max heap property. And what that means is that the parent value of a node, so the parent node, parent value is greater than or equal to child values. That means if we had this right here, if I had say 20, this might be 18, this might be 3. What about the relationship between the 18 and 3? There's no specification for that. This is not a binary search tree where we go down one path if there's a certain relationship, or we go down the other path if there's a different relationship. This simply says 20 has to be greater than or equal to 18, and 20 is greater than or equal to 3. But this also would be valid. Okay? Second property, the binary tree needs to be complete. So we need a complete binary tree. What does that mean? As we're looking at the tree, of course it takes on sort of this triangular shape of nodes. Each level is full except possibly the bottom level. And if the bottom level is not completely full, everything is pushed to the left. So we might have a node here, might have a node here, might have a node here, but then these spots are empty. Okay? So what's the benefit of this? Well, remember, we're storing this as an array. And it turns out that by having a complete binary tree, then we can calculate the indices of the child nodes based upon the index of the parent node. So let's say we have this tree. So the array that stores this have indices 0, 1, 2, 3, 4, 5, 6. So this should be centered 7, 8. All right. So there's different ways to store this, but the way you'll typically see it would be we just skip the 0 index. Technically, you could use that. Everything just will be need to be adjusted by 1. But we'll say this is 1, this is 2, this is 3, 4, 5, 6, 7, and 8. These numbers I've just written are the indices. So here's the 20, here's the 10, the 8, the 3, 7, 6, 4, 2. All right? So if I were to have, I'm going to write the value to make it more clear what we're talking about. Its index, left child, right child. So for 20, that has an index of 1. What's its left child? Well, 2 times 1 equals 2. And the right child is 2 times 1 plus 1 equals 3. There's the 2, there's 3. Look at the 10. Its index is 2. 2 times 2 equals 4. There's the 3, that's the left child. But the right child, 2 times 2 plus 1 equals 5. Well, there's the 7. Let's look at the 3. Index 4. 2 times 4 equals 8. There's this left child. And then we'll just do one more. We'll look at the 8 here. The 8 has index 3. 2 times 3 equals 6. Yep, that's what the 6 has. And then 2 times 3 plus 1 equals 7. That's the value of the 4. So because it's complete, we can do this. If instead we allowed something like this, we don't, but if we had, well, now I've got these holes, right? So how do I keep track of where things are at? I can, but typically then we would probably have pointers or something, pointing to where things are at. Something like that. All right, so how do we construct a heap? So we'll say this is our initial data. And so this would be the order in which we receive these values. So 23, 50, 45, 99, 2, and 19. And we won't do all these, we'll just do some of these. So we'll start by taking the first value, the 20. And that would be our heap. And then what we're going to do is insert additional values. So what we do is we insert new values at next available array position. What does that mean? Well, remember, we need our tree to be complete. So the next array position that's available is we're processing this a row at a time, left to right. So the next value would need to go right here. This is complete, right? Now, when I do that, in this case, we're technically done, but what we have to check is, do we still have the max heap property? $20 is bigger than 3, so we're fine. So now I want to add the 50. So 50 goes here. And now I need to ask the question, do we still have the max heap property? We don't. So this needs to bubble up, right? So that means then this will become this. And there's our current tree. So there's 50. Let's add 45. Where would that go? Well, the left child of 3, because the second row is now full. So we have 50. We have 3. We have 45. There's our 20. So now I check the max heap property. 45 is greater than 3, so they need to be swapped. And we're done. Let's add 99. So we'll start here, 50. We're using this tree. 45. 3. 99 goes here. There's the 20. And we check. 99 is bigger than 45, so they need to be swapped. So everything else stays where it's at for the moment. We check again. 99 is bigger than 50, so these need to be swapped. So as values are moving down, why don't I check, for example, that the 50 now is in the right spot? Well, remember, we started from here. 50, because of the max heap property, was already greater than everything below it. It's greater than 45, and since 45 is greater than 3, 50 has to also be greater than 3, right? Because we have 50 is greater than or equal to 45, and 45 is greater than or equal to 3. Therefore, 50 has to be greater than or equal to 3. So as something gets pushed down, it can't be in the wrong spot in the sense of now the 3 needs to pass the 50. Okay? And so we could continue this. We had 2 more values. The 2 would go right here. It would actually stay where it's at because that's fine. Then the 19 would go here. It's in the right position. So we would be done with this tree right here. Okay? What about deleting a node? Depends on where it's deleting from, right? But let's start with this tree. Right. So what we're going to do here, we're going to remove the largest element each time. Because of the max heap property, we always know the root, in this case the 70, is the largest value here. Now we could have a tie. I might have 70 and then also have a 70 on one of these. But there won't be anything below 70 in the tree structure with a greater value if we have a max heap. So let's say we want to remove the largest value. And this could be an application. We'll talk about applications in another video. But maybe we need to remove the largest value here. All right? So remove 70. Now, different people will show it different ways. Since technically this is an array, what we could do is either sort of pop the 70 by putting it to use and then overriding it with the 30, which is the last element in the array. Or some people show it as you just swap the 2 values and then I guess you do something with the 70 once you've done that. But the idea is this. We now need to replace that whole, that first element of the array, with a value, and we're going to do that by choosing the last value in the array, which is the 30. So now we have 30, 40, 20, 10, and 50. Now that we've done that, we need to check the max heap property again. We look and realize that 30 is smaller than both 40 and 50. So which one do we use? Because we have this. 30 is less than 40, and 30 is less than 50. Well, remember, the max heap property says that the parent here, this position here for the root, needs to be greater than or equal to both of its children. So we need to choose the maximum of these two, which is the 50. So this becomes 50, 40, 30, 20, and 10. Now let's say we remove the 50. So once again, we'll replace that with the last available value, which happens to be 10. I'll put them over here. So 10, 40, 20, 30. And once again, we ask the question, is this tree fine in the sense that it satisfies the max heap property? Well, no, because we have both 40 and 30 or greater. So I'm going to swap the 40 and the 10 because 40 is bigger than 30. So we'd have 40, 30 over here, 10 over here, and 20 over here. Is this fine? Well, no, because now 10 is above the 20 and they need to be swapped. So now I'm going to have 40, 20, 10, and 30. And we'll do one more. Remove the 40. So that means, once again, I take the last element. That's the 10 again. So I'm going to have 10, 20, 30. Both of these values are greater than 10, so we choose the max of those if we're doing the max heap property. So 30, 20, and 10. And we could then pop the 30, and then we don't have two more values there. Now, what would happen if for some reason we need to remove something sort of in the middle? Okay, so let's say we had something like this. We had, 50, 40, 30, 10, 20, 15, 16. Okay, let me check and make sure, since I'm making this up on the fly, 50 is greater than 40 and 30, 40 is greater than 10, 20, 30 is greater than 15 and 16. So let's say for some reason we need to remove the 30. What do we do? Or let's put another value down here. We'll call this 5 and 8. Well, we do sort of what we did before. We replace this value with the last value. So to do that, we'd have 50, 40. Now we have 8 here. 10, 5. Okay, so remove the 30, replace it with the 8, because that was the last element in the tree. Check the max heap property, and it's not correct. Now here we have a potential issue as compared to the remove the root. It's possible because we don't have a relationship between the 40 and the 30, that is the left child and the right child, other than them both being less than or equal to the parent. In this case, I happen to have that the 8 is larger than these two values, so now we'd swap, and what would happen here, I'm just going to look at this part. What would happen here is we would then end up with the 16 and the 8 and the 15. But when we're removing certain things like that, depending on where you're removing the piece, there's always a possibility that what you replace it with is actually larger than the thing above it. So if that had been the case, it couldn't here, right? Because the 8 has to be less than the 50. But if I'd had something else, I don't have a good example here, but there's a possibility that something over here was still bigger than some of the values that need to move up on. So let's say we're removing the 16. Oh, here, we'll take this. Let's say we had we'll say this was 50, 45, 44, 43, 42. So this right here is 10, because that's less than 50. And then we have 8 and 7. So 50 is greater than these two. So let's say we said remove the 7. Well, we put the 42 there. And I'm just going to draw part of this here. But 42 is greater than 10, so this needs to actually move up. And then the 50 would be up here. And the rest of this would be the same. Okay, so there's the basics of a heap. I've shown insertions. We use the insertions for constructing the tree. So whether I'm doing it from scratch, like I did here, or if I've already got the existing tree, which essentially is what I had, at any point here, I've already got the existing tree that meets our heap requirements. Anytime you want to add something, you put it in the next available spot. And then, like in this case, if we have these two nodes, you'll hear and then see, well, how's that fit into the rest of it? Does it need to bubble up, or what needs to happen to it? So that's a heap.